Hello, in this session we'll go with third year group elements of P black. Boron, aluminium, gallium, indium, thallium constitute third year group elements, also called 13th group elements. The general electronic configuration will be Ns2np1. Aluminium is the third most abundant element on the earth crust. Gallium is having highest liquid range, so it is used in high temperature thermometers. Ionization potentials, if you see, boron is greater than aluminium, but aluminium is less than gallium. Then gallium, indium, again it is decreasing, indium to thallium, again it is increasing. So this is very special order, you need to remember this. Inert pair effect is shown by thallium, +1 oxidation state is more stable than +3 due to reluctance of Ns electron pair to take part in bonding, that is because of lanthanide contraction. So the common oxidation states are +1 and +3. Down the group, the +1 stability increases and +3 stability decreases. This is applicable for group 13, group 14, group 15. Higher oxidation state stability decreases, lower oxidation state stability increases. Boron is a non-metal, aluminium is a metal. Boron is a poor conductor, aluminium is a good conductor. Let us see some more properties here. Chemical properties of group 13 elements. Halides. MX3 type of halides they form. About their Lewis acid strength is very interesting. BF3, BCl3, BBr3, Bi3. If you see, Bi3 is more acidic. The reason is BF3 has back bonding. Boron, fluorine almost of same size. Because of this, back bonding ability is maximum in case of BF3. So it is a weak acid. But if you consider boron, aluminium, gallium, indium, boron acids are better. BX3, ALX3, GAX3, INX3. Oxides, B2O3. B2O3 is weakly acidic. It is H3BO3 acid, boric acid. Aluminium, gallium oxides and hydroxides are amphoteric. Indium, thallium oxides and hydroxides are basic. So down the group the basic nature increases, down the group the metallic nature increases. Boron oxides and hydroxides are acidic, aluminium oxides and hydroxides are amphoteric, indium and thallium basic. Aluminium is the most abundant metal in the earth crust. Its minerals are Al2O3, 2H2O is bauxite, corundum is Al2O3, diaspore is Al2O3, 1H2O, gibbsite is Al2O3, 3H2O, crierate is Na3AlF6. Feldspar is K2O, Al2O3, 6SiO2, mica is Cal3O8. You can write like this, otherwise KAlSi3O8, OH taken twice. Beryl B3Al2Si6O18. These are the important minerals. Extraction of aluminium from bauxite. Bauxite has two types, red bauxite and white bauxite. Red bauxite means which contains iron oxide as impurity. It can be purified by Bayer's process by adding sodium hydroxide. This you can say one type of leaching process. Fe2O3 basic in nature, so won't react with sodium hydroxide, but Al2O3 amphoteric, so it dissolves in sodium hydroxide to form sodium meta-aluminate NaAlO2, you can see in the equation, which then reacts with water to form aluminum hydroxide, which on heating gives Al2O3 pure Al2O3 is formed. This is one method. The other method is Hall's process. In place of sodium hydroxide, you just use sodium carbonate, rest everything is same. Surface process is for white bauxite where the impurity is silica, SiO2. So it is treated with coke and nitrogen, where coke reacts with silica to form silicon vapors and carbon monoxide. Al2O3 reacts with nitrogen and coke powder and get reduced to ALN, aluminum nitrate. Aluminum nitrate further hydrolysis gives you aluminum hydroxide, which on heating gives you pure Al2O3. So these three steps are to remove iron oxide or silica impurities. Electrolysis of Al2O3. Al2O3 is not a very good conductor. To increase its conductivity, Na3AlF6 is added, cryolite, and to decrease its melting point, CaF2 is added, fluorospar. To decrease melting point and to increase the conductivity, these are added. Then at cathode aluminium, at anode oxygen gas are obtained from Al2O3. In this one question they will ask you repeatedly, we need to replace the anodes, that is carbon rods. The reason for that is the releasing oxygen gas will react with coke. Refining of aluminium, Hoops process. Pure aluminium is cathode, impure aluminium is anode, impure aluminium will be at the bottom, pure aluminium will be at the top. Cryolite plus BF2 is the electrolyte. Like this we can purify. Whenever we are purifying metals by this type of technique, Hoops process of technique, impure metal is always anode and pure metal is always cathode. Remember this method. Sorry. Properties, if you see, aluminium reacts with dilute HCl or H2SO4 to form hydrogen gas. With concentrated H2SO4 SO2, but with concentrated HNO3 it becomes passive due to protective oxide layer. Aluminium reacts with alkalis to release hydrogen like sodium hydroxide, dilute sodium hydroxide, sodium metaluminate, concentrated sodium hydroxide, sodium aluminate, NaAlO2 metaluminate, Na3AlO3 aluminate. It reduces less electropositive metals like iron oxide, manganese oxide, chromium oxide. Here mentioned is Fe2O3. Fe2O3 can be converted to Fe. This method is called Goldschmidt aluminothermic process to repair railway tracks. Alloys of aluminium, aluminium bronze, duralumin, alnico. You can see the combinations here. Compounds of aluminium, AlCl3. AlCl3 happens to be a dimer. Dimer structure you can see here. Lewis acid, because it can accept a pair of electrons. Its aqueous solution is acidic because it is made up of a weak base and strong acid. Al2O3 is another important compound. Al2O3 are used generally as gems, rubies, sapphires, topaz, emerald and amethyst. Based on their colors you can remember them and you can be asked a question. Rubies are red, sapphires are blue, topaz is yellow, emerald is green, amethyst is violet. Alum salts, X2SO4, Y2SO4 taken thrice 24H2O, where X is monovalent cations like sodium, potassium, ammonium. Lithium cannot form. Remember this point. Lithium cannot form because of small size. Y plus 3, aluminium, iron and chromium. Potash alum, K2SO4, Al2SO4 taken thrice 24H2O. It is also called common alum. Its aqueous solution is also acidic in nature, similar to AlCl3. Uses purification of water by coagulation. Styptic as the meaning of styptic is for stopping the bleeding. And mordant mordant means color fixing agent. In textile industry it is generally used. Boron minerals are borax. In India it is called Tingal, Na2B4O7 10H2O. Kernite, Na2B4O7 4H2O. Boric acid, H3BO3. Colemanite, Ca2B6O11 5H2O. Borax, Na2B4O7 10H2O is basic in nature in aqueous solution because it is having sodium hydroxide. But Na2B4O7 on heating gives NaBO2 and B2O3. B2O3 is utilized for borax bead test. With metal oxides it forms different colors. For example, cobalt bead, blue color, copper bead, blue color, chromium bead, green color, nickel bead, brown color, and manganese bead is pink color. Borax bead test. Boric acid, H3BO3. H3BO3 is a monobasic acid, but it is not a proton donor because all protons are busy in hydrogen bonding, so this cannot release any proton, but it releases proton when it reacts with water. The proton is coming from the water. H3BO3 plus water gives rise to H plus and BOH4 minus. Here it is sp2 hybridized trigonal planar structure, boric acid. Boron hydrates, B and Hn plus 4 type are called nidoborans, B and Hn plus 6 type are called arachnoborans. B2H6 when reacts with ammonia it forms diammoniate of diboran, B2H6 2NH3, which on further heating gives B3N3H6, which we call borazine, inorganic benzene, isoster to benzene having same number of electrons, same number of atoms, isoster you can call B3N3H6, borazole or borazine. Both boron and nitrogen are in sp2 hybridization. You can see the structure here, very similar to benzene. Structure of diboran is again important. Here 2 boron atoms in the plane, 4 hydrogens are in the plane, 1 hydrogen is above the plane, 1 hydrogen below the plane. Those 2 hydrogens are called banana bonds. That bonding is also called 3 center 2 electron bonds or tau bond. Banana bonds are tau bonds above the plane and below the plane. These are the important lines of third group elements. We'll discuss 14th group elements in next class. Thank you.